Here's the answer key for the quiz on electron dot structures. Question 1 said how many lone electron pairs are around the central atom in a molecule of H2S? So we got to draw it. I think you'll find that for a lot of the structures eventually on the summative, the question might seem really simple, but you're going to need some scratch paper so you can draw the structure. Sulfur has 6 valence electrons. 3, 4, 5, 6. It's in the group with oxygen. So 6 electrons, valence electrons, are organized as 2 pairs and 2 singles, which makes sense because then my single electrons can share with hydrogen. Hydrogen's got 1 valence electron. My hydrogen only need 2, so they are full in the first 1s orbital, and my sulfur is also full with an octet. There are 4 bonding electrons and 4 non-bonding electrons. Or we could say that there are 2 lone pairs of electrons. Lone pairs meaning they're kind of all by themselves. They're not in a bond. Question 2, which will contain a double bond? Now, to some extent, maybe you wouldn't need to draw these. And if you think about hydrogen, you can draw them. Hydrogen's only got 1 valence electron and only needs 2. So hydrogen's probably only going to make 1 bond. Yes, it does. So you might be able to just kind of think about that in your head without drawing it. Hydrogen only needs 1 bond. So I'm never ever going to think about double bonding a hydrogen. Same thing with the halogens. Halogens like chlorine. Chlorine with its 7 valence electrons. 6, 7. Well, it's trying to get 8, so he only needs 1 more. Now, obviously, you could draw the dot structure, but again, maybe just by thinking it through, you'd be like, well, if I already have 7 valence electrons and I'm going for 8, I only need 1 more. I'm never going to think about double bonding a halogen. That's not going to be my first thought. Now when I get to something like oxygen, then I start thinking that, yeah, maybe now we could double bond. Oxygen's got is 6 valence electrons. There are 2 pairs, 2 singles. Got 6, looking for 8, needs 2 more. So yeah, now this is the family where I first start thinking about the possibility of a double bond. And if I do draw the other one, it's a little bigger. That's okay. I'm going to kind of rig it so that the single dots line up because I know that's where I want the bond to go. So I'm going to connect the dots once, connect the dots twice, double bond. So there's my answer. When I think about nitrogen, now is the first time I'd start thinking that a triple bond might be a good option, where nitrogen has 5 valence electrons organized as a pair and 1, 2, 3 singles. But again, I'm going to kind of put the singles toward the middle because I know that's where the bond is going to go. So nitrogen, nitrogen, I'll kind of line up those singles and I'll put the pair on the outside. And now I can triple bond. 1, 2, 3. That's the first group where I really start thinking that a triple bond could be a possibility. Carbon could do anything. For example, question 3 says as more electrons are shared between 2 atoms, the bond becomes stronger. For example, triple bonds are stronger than double bonds and single bonds. Yeah, the more electrons shared, the more energy it's going to take to separate them all and break the bond. So we want to know which of the following molecules will have the strongest bond between the carbon atoms. In other words, which of these might have a triple bond? Can you predict by looking at the formula? Maybe, but you might just end up sketching them. So we've got carbons and hydrogens. The element that can make the most bonds always goes in the middle. And if you ever see a carbon, that's your guy. The carbon can make 4 bonds. He's going down first with 1, 2, 3, 4 valence electrons. Then I'm going to get the other carbon in the middle. Sometimes they call this the carbon-carbon backbone. And the 2 carbons make the most bonds, so they go in the middle. Now, of course, I have to connect the carbons. So we could at least connect them in the center. The first one is C2H4. And so I've got, it looks like 6 places where I could put something, but I only have 4 hydrogen. So it really should be fair to each, and we should split up the hydrogen 2 and 2. Molecules are most stable when they're symmetrical, and so you can put those 4 hydrogen wherever you want, as long as we put 2 on each carbon. There we go. 1 and 2. And now I can see what's left. Wow, yeah, each carbon still needs 1 more bond, so we can just link them up twice. So the C2H4 is a double bond, which isn't bad. I mean, it's stronger than a single. And the second choice in the middle is C2H2. I draw my carbon with its 4 valence electrons. I bet you can see where this is going, right? Get out of there. 2, 3, 4. I might as well connect them somehow. But now if it's C2H2, I only have 2 hydrogen. So again, I should give 1 to each carbon. That would make it most stable. I'm kind of going to put them on the outside because I'm going to leave spots in the inside for the carbons. Each carbon still needs 2 more bonds, so we can link them up again. Here's the triple. The C2H2 is the triple, so I'm assuming this is going to be the strongest. I guess just for fun, I could draw the C2H6, but I bet you kind of know where we're going with that one, huh? Here's my carbons with their 4 valence electrons. We're going to link them up at least once. Oh, okay, I got it. Now there's 6 more dots. I need 6 more bonds. And in the last option, we've got 6 hydrogen. So now we just put hydrogen on all of the open spots of carbon. The carbon in the middle of each structure will always have 4 bonds in some capacity. There will be 8 valence electrons on each carbon. He needs that octet. And then each hydrogen in any of the structures will have his little duet, 2 valence electrons, filling the first energy level. Questions 4 and 5 are giving you some structures, and we want to know which is correct. Question 4, which is the correct structure of PBr3. So now normally if I were drawing phosphorus, I know there are 5 valence electrons. It's underneath nitrogen. And normally I put that pair on the top. If I see that like phosphorus is probably going to be the central atom. And then I'm going to hook on my bromine. Perfect. There are 3 bromine and there are 3 open spots on the phosphorus. I'll purposely line up the singles. Bromine's got a total of 7 valence electrons. Connect the dots. Hopefully these structures start to become a little more intuitive. The more you draw them, you kind of see some patterns that, I mean, this would be the same structure if I had nitrogen in the middle. It would be the same structure if I had chlorine on the outside. As long as you've got atoms that have the same number of valence electrons, you're going to end up drawing the same structure. And now here might be what I would have drawn. And none of these 4 structures are exactly the same. They've all got the lone pair off on the right-hand side. But that's totally fine. In real life, this is a 3-dimensional molecule that I can twist and turn and flip and flop. And if I could hold it, I mean, they're like beyond microscopic. But it's okay to like turn this a quarter turn. And so I'm just trying to find the structure that's got 3 bonding groups on the phosphorus, 1 lone pair, and then around each bromine, there's 1 single bond and then 3 lone pairs. So it should end up being this first one. In the second one, my bromine do not have an octet, and they need an octet. Those extra electron pairs are essential on the bromine. The third one is just chaos. How many bonds did they put on that phosphorus? That's insane. Well beyond an octet. And they still don't have an octet on the bromine. And kind of similar with the last choice, even though the bromine have an octet, you've got more than an octet on the central phosphorus. Question 5. Again, something kind of similar, that if I were drawing this on paper, I might start by drawing my carbon. And he's got 4 valence electrons. Fantastic. Well, I've got 2 hydrogen. Okay, I'll just connect those. Single bond, link them up. And then I see that there are 2 more electrons on carbon, which is perfect because oxygen typically need 2 bonds. And so when I draw my dots on oxygen, I know there are 2 singles. And I'm going to purposely line them up with the singles on carbon. And then there are 2 lone pairs. Here's my 6 valence electrons on oxygen. And then I'll connect the dots. Now, again, my drawing does not look like the 4 that are shown. And that's something that we'll get into in the next section of this chapter, that a Lewis dot structure, these electron dot structures, just have to show that everyone who wants an octet gets an octet. And if you were ever unsure, you could count the number of valence electrons, and that's the number that you should have represented in your structure. So for example, if I thought this looked really funky, I could say, well, carbon has 4 valence electrons. Hydrogen has 1, but there are 2 hydrogens. And oxygen has 6. So if I add them all up, 4 plus 1 times 2 plus 6, I've got to use 12 total electrons and distribute them so that everyone gets a full outer shell. So my carbon is full, 2, 4, 6, 8. All 8 are bonding electrons. My oxygen are full with 8. There are 4 bonding and 4 lone pairs. And my hydrogens are good. They each have 2. Those are the only rules of an acceptable Lewis structure. I've given octets to whoever needs them. I filled up the hydrogen with 2, and I used 12 electrons. Now, in the next half of this unit, we'll talk a little bit more about like how the angles are arranged. So, I mean, in general, when I'm picking the right structure here, I want a central carbon with a double bond, 2 single bonds, and I want 2 lone pairs on the oxygen. It's okay if the angles are a little bit different, because again, I'm drawing something that's 3-dimensional. This is like a 3-dimensional structure, and I'm trying to draw it on paper. So if my angles aren't perfect, that's okay. But I've shown the backbone of this molecule and how the bonding occurs, how we get our full outer shells. Question 6. Which of the following molecules will have a central atom with a deficient octet? That just means less than 8 valence electrons. And so again, it might help to draw them. If I have H2O, whatever can make the most bonds goes down first. That's going to be my oxygen. Hydrogen and halogens will never be in the middle because they only take 1 bond. But my oxygen can take 2. But he still has an octet. Even though he's got 2 bonds and 2 lone pairs, it still counts for 8. Now I've got carbon, 3 hydrogen, and a fluorine, but carbon makes the most bonds. Hydrogen and halogens are always on the outside. Now you can hook these on wherever you want, but somehow I'm going to add the 3 hydrogen, 1, 2, 3, with his 1 valence electron, and then the fluorine. But you can put the fluorine on any spot. It could be on the top, on the bottom. That does not matter. Nope, my central carbon still has an octet. NH3. Nitrogen has 5 valence electrons, a pair and 3 singles. Perfect. I have 3 hydrogen. After a while, there are some structures where you'll be like, oh my gosh, I've drawn this a bazillion times. Even though he only has 3 bonds, it still has an octet. That lone pair is essential to proving that nitrogen and oxygen do have a stable outer shell. So then hopefully it's boron, huh? Boron, oh, I bet it is. He's only got 3 valence electrons. And I do have 3 hydrogen. 1, 2, 3. But there's my winner. Boron has the deficient octet. He's only got 3 valence electrons, and he's just going to bond those 3, leaving him with less than 8 valence electrons. But there are some elements that are stable with less than 8. Number 7, CO2 is 2 double bonds. The carbon in the middle has 4 valence electrons. I can add on an oxygen, and again, we'll kind of line up the singles because we know that's where the bonds will go. 5, 6. Aha! Oxygen needs 2 bonds. Let's give it to him. Now when I draw the other oxygen, again, I'm going to kind of rig it. I'm going to put the single dots so that they match up with the single dots of carbon. And then we can double bond it again. Somehow carbon is octet for life, whether it's 4 single bonds, 2 double bonds, a double and 2 singles, a triple and a single. But oxygen is always going to get that octet. So here we got 2 double bonds. And it's okay that my oxygen kind of look a little different, that it looks on paper like my dots are a little different. No worries. And the last one, which of the following is not a proper electron dot structure? So first I'm looking for octets, except for hydrogen. Obviously hydrogen only needs 2. Or when you look at these types of structures, a dash represents a single bond, which would be the sharing of 2 electrons. 2 dashes would be a double bond, or the sharing of 4 electrons. So for example, like in this top structure, oxygen is good. He's got 2 double bonds. That would count for 4 electrons, and then 2 lone pairs. 4 and 4 is 8. My carbon are good. 2, 4, 6, 8, 2, 4, 6, 8. And my hydrogen have a single bond. That would be 2 electrons. The middle or the second structure is fine. I'm looking at my carbons. They all have 4 bonds. That would represent a total of 8 electrons. My hydrogen are all good with 1 bond. And my oxygen has 2 bonds and 2 lone pairs. That adds up to 8. Now it's this third one. Do you see the problem in the middle? Whoops. Get out of there. That oxygen does not have an octet. He's going to need an extra lone pair. The carbon are fine, the hydrogen are fine, but oxygen's got to have an octet. Kind of like he does in the last one. If oxygen has 2 single bonds, then he's going to need 2 lone pairs.